Node.js, JavaScript fundamentals, hands-on training, and workshops. Computer science in front-end development. It's for more than just interviews. With Jem Young.
Hey everyone, I'm Jem Young. I can't see you because my screen's set up. Whoa, super meta. Anyways, I am here to talk about computer science for front-end land. And computer science can be a bit scary, but we're going to go slow. We're going to go nice and slow. I know it's been a long day and you've learned a lot of things, many things, and your brain's probably hurting right now, but I think computer science is one of the more important topics because it's the foundation of everything that you've learned today. Like every single thing that you're going to do on a computer, at some point, some smart person, maybe you in the future, has or will come up with a solution to it. And it involves thinking about it analytically. So I will paste this link for my slides into the chat. Excuse the meta-ness of this. Pop you out. And there we go. Should be good. You share. And I'm going to post those links in there. Make sure we can see it. I see some random animals, as Google calls them, in there. Cool. So today we're going to be switching back and forth a lot between my slides, Brian's notes, and just different examples and web pages that I found interesting and that are super helpful. But before we get started, I should introduce myself. I'm sorry, that's incredibly rude of me. I am Jem Young. I am a senior software engineer at Netflix. I work on the UI team. But I do a lot of non-UI stuff. So that's why my title is Senior Software Engineer, not UI Engineer, because while I build UI, I do a lot of Node and backend things. And yeah, today we are live here at Netflix. It's just a standard work day. It's just a Friday. I had a good breakfast. Anyways, enough about me. I am here on behalf of Brian Holt, who, because he's a rock star and he's super busy and globe traveler and all these things. He could not be here. So he asked me to step in and says, Jem, you do some computer stuff, right? I'm like, yeah, I do. And I used to work with Brian. And I'm really passionate about giving these kind of courses to computer science because a lot of people are intimidated by it. And they see a lot of weird notation and words like algorithms and hash maps and things like that. And it seems scary, especially people that aren't trained in CS or have come from a boot camp or are self-taught. It's really approachable if you start off from the right level. And that's what I want to do today. Just kind of lay a foundation. Now, 2 hours is not even close to enough time to cover even a fraction of the topics in computer science, but I'm going to extract a lot of the high-level concepts, and we're going to do some exercises together. And once you do the exercises, you'll see that, it's not that bad. It sounds scary if someone just whiteboarded it for you, but it's really not that bad. Before I keep going, I should give a quick shout out to Azure Advocates. They're awesome. They provided the diversity sponsorship for this, so thumbs up to them. And that's a sweet raccoon/cat with a mask on. Pretty sure that's a raccoon. Sorry, I've never given a live presentation. I'm used to speaking in front of large crowds. So I'm just going to assume you're laughing every time I crack a joke. I was waiting for laughter there. Today, we're going to cover a few topics. We're going to cover why computer science. We're going to cover things like algorithmic complexity, which sounds complicated, but it's not too bad. We're going to cover searching, which is very important. Cover sorting, recursion. Then we're going to finish with data structures, because data structures kind of lay the foundation of how you want to think about the things you want to build at the end of the day. But we need to build up to it first. So Azure Advocates, again, super awesome. And let me just pop Windows real fast to make sure there are no questions. Sorry, I'm on one screen right here. Someone asked, did Netflix feed you that breakfast? Yes, they did. On Fridays, there is hot breakfast at Netflix. Usually it's like a buffet or something, but today is hot breakfast day. But normally I work from home on Fridays, but I want to come to the office because, well, you all are awesome. And I want to get like a solid Wi-Fi connection that I knew would not mess up at all. And hopefully everybody can hear me. Got my fancy mic here. I don't have a Ken C. Dodds mic because he's like superstar, that sort of thing. But I do the best I can. All right. All right. Let's dive in even more than I just dove in. All right. So why computer science? Why is it important? Well, computer science is actually an old science. It's been around for maybe 100 years. No, it's hard to say. So the foundation of all computer science is math. So you can argue computer science has been around for hundreds and hundreds of years, as long as people have been thinking about math, people have been thinking about some sort of computation. And fun fact, back in the day, I know that's not an exact time frame. Back a long time ago, a person that did manual calculations by hand, they were called a computer. Like they literally computed numbers. That's where the term computer comes from. Obviously, that's not something we use today. We have laptops and shiny boxes and things like that. But computers are just things that can perform calculations over and over again. They do repetitive tasks. They add things, divide things. Mostly they manipulate numbers all around. But the idea of computer science is one that, when we talk about modern computers, has been around, say, 100 years. We'll say that. But what it is people said, hey, I have this machine that can do things over and over and over again. And that's cool. It can add these numbers over and over and over again. Okay, what else can we do with that? And that sort of thinking about like, what else can we get this machine to do over and over and over again that it's really good at is the foundation of every single programming language. It's every single technological advancement regarding programming. That's where it all comes from. Just let's make the computer do as much work as possible. And that's good. It's good. But if we think about computer science, we think about things like, how can we make it more efficient? How can we map our world in a way that makes sense to humans, but also translates to computers as well? And that's essentially what computer science is at the core. It's saying, what's the most efficient way to get this thing done, but in a way that I understand it as a human, and that a computer can understand it so that it's efficient. And turns out it's a very deep and broad subject. But unfortunately, especially when we talk about JavaScript and UI, we see computer science as kind of this weird black box that you only need to know for interviews. And that's not right. If you ask Brian Holt about how he feels about whiteboard interviews, you will hear about an hour or 2 hours, maybe 3, depending on how many beers you buy them, on why they're dumb. And that's because people approach them kind of thinking about the wrong idea. They think of this scary notion of, I need to know all these formulas. I need to know what big O and big beta and big omega. And like, I need to know how to do a heap store on a hash map. And I'm like, all these things. But no, computer science is just pattern recognition, really. If you're a good computer scientist, you see like, oh, I need to implement a least recently used cache. That's hard. I'm going to use a linked list because that's my go-to. And it's that sort of thinking that makes computer science powerful. So today, I don't expect you to learn every single thing that I talk about or memorize it and take it for gospel. It's more next time you see a problem, you'll say, oh, I need to use a set for that because this would be a perfect application of a set. It's about thinking about these problems on a really, really base level. All right, I will switch back to my question screens in case there's any question. Adrian, laziness. Yes, a good engineer is super lazy. The best engineers I know are lazy. Why invent a wheel again when the wheel's been invented 100 years ago? And that's really what we want to learn today is things that have already been invented and new ways to think about the problem. So let's start with an easy-ish topic, the topic of complexity. So if you see an underlined link, you will link and you'll see Brian holds awesome notes for 4 semesters of computer science in 6 hours. And he goes into, I know I'm scrolling fast, don't worry. He goes into a ton of detail. And then you're like, oh, I already know this stuff. There's part 2, even better. Part 2 is way, way more detail. And we're only going to touch a little bit in part 2 because it's a bit complex. And especially after a long day of listening to smart people, as you've been doing all day, I don't want to blow your minds too much. Let's take it nice and slow. But let's start with complexity. Complexity we describe in terms of big O traditionally. Big O, actually, so now I'm going to draw. If you can't see me, just kind of, I don't know, yell. But we talk about big O. It's a way of describing the complexity of an algorithm. So something like we want to do a linear search on an array. So I've got an array of, let's say, 1, 2, 3, 4, 5. Right, standard array, not super complex. If I wanted to search for the number 4 here, we can do a linear search. And a linear search is pretty good. A linear search is going to look something like this. And that is, linear search is big O n. Because all big O n is saying is that as my array grows, so if I said 6, 7, 8, 9, 10, a million, it's going to take this long, this long, this long, this long, and it's very predictable. And that's all big O is saying. It's saying the most amount of time I'm going to spend doing something, that's what we're going to do. That's what we're covering. So that's big O. I will talk briefly about big beta and big omega, but actually I won't. That's a bit too much for now. Okay, so to reiterate, if I'm doing a linear search on something, big O n. N is just the size of your data set. So as big as my data set is, that's how long it's going to take. Linear search, so it's going to be 1, 2, 3, 4, 1, 2, 3, 4, something like that. Now, you're saying that wasn't that useful, Jem. I am a JavaScript expert. I am a superstar at JavaScript. That's not that useful to me. Yeah. So simple searching an array, that's pretty straightforward. What about more complex algorithms? What if you had something that was a nested for loop? What if you had a for loop searching over for loop? What if I had an array of arrays of arrays of arrays of arrays? How do I describe that? If you're talking to your peers, you wouldn't say, oh, it's pretty fast. That's not useful. You can't describe things relative to your current experience. So we have that's where the idea of big O's come, time complexity. It's saying that it doesn't actually matter what the overall structure looks like. Here's how fast it's going to run in actual time. So I'll show you an awesome website, and it does a much better job explaining this. And I stole this directly from their website and link at the bottom here. So remember how I said big O n right here? It runs at like fairly, it's linear time almost. that's one of the better ones. And a lot of things we do, we might hit Big O later. Well, sorry, we'll talk about it. But if we click the Big O cheat sheet, which is a fantastic site, we see all of these things. We're going to talk about data structures a bit. We're going to talk about sorting algorithms in a little bit. And I'm just going to switch over real quick. Oh, there's a glare. Thank you. I'm actually really tall. You can't tell. So I'm like sitting low in a chair. So let me try that. Okay. There we go. Back to complexity. Yeah, so Big O is a way of saying it's the upper bound on describing the complexity of a given algorithm. There's also Big Omega, which describes the lower bound of an algorithm. But in general, you don't care about the lower bound. You're just saying like it's going to run no slower than this or no faster than this. Big O is a way of saying like it's not going to run any slower, because that's what we care about. When we're building large scale production systems with millions and billions of queries, things like that, and we're having an algorithm that says, I don't know, sorts over username, you want to know how fast that runs. Now, if I said my algorithm's super fast because I have 50 people in it, cool, but that doesn't help you at all, because you, I don't know, you work at Omega Corp. It's a cool company name. You work at Omega Corp and you have 1 billion items in your user base, and you need to figure out how to sort all of them, or you need to iterate over all of them. So my little algorithm that I said, it runs pretty fast at 50, that's totally relative to my speed. That's where this whole idea of Big O, because we're describing the overall trajectory of an algorithm. So if something's really small, it's going to be around here at the bottom part. So it doesn't really matter. If you have like 1,000 items in an array, it doesn't really matter kind of the algorithm you're using as much. Now, if you had 1 billion, you're somewhere out here. This is where the complexity of the algorithm that you choose matters. So if it's strictly linear, it's going to be over here, which is pretty long. If it's factorial, never do things factorial. Factorial is, it's one of the worst complexities you can run. Factorial is a way of saying factorial 5 is 1 times 2 times 3 times 4 times 5. So you can imagine that's not very good for anything. But this site is awesome, explains a lot of things. I just want to touch on Big O because we're going to talk about it in terms of how long it takes to search over something, or how long this algorithm takes, because it becomes really important. Again, at very, very small things, like 1,000 or 1 billion, actually it doesn't really matter. At small data structures or small elements that you're operating on, the Big O time doesn't matter as much, because as we see at small, they're all kind of clustered here. But as things grow, as we scale our programs that we're building, it becomes much more important. And that's what I want you to think about today, is building things at scale, because at small scale, a lot of decisions we make regarding CS fundamentals, they don't matter as much, because you're not going to see the impact. If I choose BOGO sort instead of merge sort, you may not see the impact because it's just too small. But when you get to 1 million and you say, why is my server crashing, or why is it running out of memory? And someone says, your algorithm is Big O and log n. They're like, that's pretty good. But if we can get it down to Big O n, that would be superior. So I will pause. Does it make sense so far? Any questions? Kyle has the right idea. Why ask for 1 billion when you can ask for 1 million? Yes. I'm sure if you've never seen Big O before, again, this website is fantastic. If you have seen Big O before, then I'm just kind of rehashing old ground. But in general, at some point in your career as engineers, you're going to see things described like this. But now you know exactly what you're talking about. In fact, you don't even have to memorize these. You can just look at that chart and say like, something's n log n. That's pretty fast, actually. Whereas something's n factorial, that's pretty bad. Okay. Let's talk about searching. Okay, I'm going to go back to the whiteboard because whiteboarding is awesome. All right, here I am. I don't know if you can see me. Is my head cut off? It probably is. It's okay. Searching. Let's talk about searching arrays mainly, because a lot of data structures, hash, we have trees, but let's focus on searching arrays right now because that's something we do a lot, but it illustrates good CS principles. So let me draw down here. I've got an array of 1, 2, 3, 4, 5, 6, 7. Actually, I'll make it easy. Actually, 7's fine. So what are the two ways that I have to find 5? Well, there are two basic ways to search an array. We can go linear, or we can do something called a binary search. Binary search sounds complicated, but it's really not. But let's do the linear search first. So linear search looks like, I'm going to check 1, no, 2, no, 3, no, 4, no, 5. All right, we found 5. We found in 5 iterations. But let's say our magic array that keeps growing, it goes dot, 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 I don't know, 10 billion. Someone told me a rumor that's how much Kyle Simpson gets paid to speak. It's probably true because he's amazing. But let's say it's just this insanely large number. Because, again, let's think back to Big O. When we're thinking like, oh, Big O time doesn't really matter. Yeah. Draw this little mini graph here. Remember, linear time looks something like that. So as the array grows, the time grows. So searching 5, that's going to be about probably here. It doesn't really matter. But when we get to 10 billion, this thing grew so far because it's unbounded. We get here, that's going to take a long time. So linear search, if you're talking about a very small search, linear search can be fine. Depending on the size of your machine, depending on the size of your array, you could probably even search probably 1 million items linearly, and you'd probably be okay. JavaScript is really fast. Computers are really fast. But there's a better way. There's a faster way to search through this array. So when you finally get to 10 billion trillion, there's something called binary search. Yeah, binary search. Binary search is awesome. The idea of binary search is you have a sorted array. So all these items are already sorted. And you're saying, I'll give it a 10 billion for now. In binary search, it sounds cool because it makes you sound like really smart. You're like, yeah, I did a binary search on something. It's better to just think of it as like half and half and half and half search. But that's not as sexy. Computer scientists like to use big words because it makes them sound smart. And you can do that too. But the idea of binary search is saying, I've got this sorted array. I know it's length 7, so I'm just going to split it about here. And we're looking for 5 still. Is 5 more or less than 4? It's more. So instead of searching the rest of this array, cut it out. So now let's split this array. So we've got 3 items left in this array. Let's split it in the middle at 6. Now, is 5 more or less than 6? What's less? Bam. So we found that in, what was that? 1, 2, 3 steps. Versus if I did a straight linear search, it would be 1, 2, 3, 4, 5 steps. So even on a small array or a small item, we can see that binary search is far superior to linear search. Is it easy to build? Yes, it is. We're going to be doing that in a second. But binary search runs at big O log n. Everybody can see that this marker is not very good. So remember, linear search, everybody can see that. Linear search was big O n. And we remember what that looks like, right? I'm going to switch my screen because I can't even see what you can see. That's okay. Even better. Oh, I've got so much room. I got room over here. Remember, a linear search looks something like this. That's okay until we get to really, really, really big numbers. Now, binary search looks something like this. Ooh. So when we get to a billion, it's way out here, binary search is still just going to be here. And remember, every time you see log, just think it's dividing and dividing and dividing. So the thing you're searching over, your n, your data set, is getting smaller and smaller and smaller and smaller. That's what you think. That's what a log scale means. Okay, I have talked a lot, but now let's implement binary search. Because it sounds fancy, and it's not. All right, switching back. Let's implement a binary search. So I'm just going to click on the link. Brian has an excellent, he has excellent notes that go into far more detail. But remember, the formula for binary search is take the array, a sorted array, cut it in half, say, is the thing we're looking for bigger or smaller than this pivot that we've chosen, the middle? If it's smaller, then we're just going to search this array. And we're just going to do that over and over again until we either find the element or it doesn't exist. So if you click on the link for the exercise, Brian has a fancy, oh no, okay, it froze for a second. So I'm gonna give you, let's say 8 minutes. I know, what an arbitrary amount of time to code something. But he's done a lot of the code already. So go ahead and implement binary search, but think in your mind, remember it's splitting half by half by half by half. I'll give you a few minutes. Because once you implement binary search the first time, you'll say, oh, okay, that makes total sense. So is everybody with me? I clicked on the link for searching. And then I just scrolled to the exercise here. And it does have the link for the completed exercise as well, but try not to cheat. I'm telling you, if you just take the time, the 7 minutes now to do this, it will make so much more sense to you. And I am going to go grab a soda. My throat's getting dry. Be right back. Yep. And just reading through these questions. Yes. Kyle makes an amazingly on point. There is a balance between planning your future development against over-engineering. what I see a lot of people new, especially new in UI land, is probably over engineering things. They say, oh, well, I heard this new shiny framework, Vue, Angular, React, and I need to implement that. And then they have all these tooling and they have this giant complex system when all they're building is a simple static hello world page. So yeah, everything you ever learn from now on, make sure that you understand the trade-offs that you're making when you do it. Binary search is a pretty straightforward implementation, and it's pretty useful. There are more complex algorithms that we're going to cover that may or may not be worth implementing, but it depends on the size of your data set. It depends on how big you want to scale in the future. If I was starting a startup, I'm not going to get on Amazon and have like 4 extra large memory instances that are running like 80 NVIDIA CUDA processors. I just don't need that yet. But I should always build with that sort of thing in mind. If that makes sense. It's so weird talking to a computer. Sorry, it's hard to say it because I normally can gauge someone's reaction like, what he's saying makes a lot of sense. Or like, I have no idea what he's saying. But here, I just have to kind of hope that you know what I'm saying. It's so lonely in here. Just a giant room by myself. All right. Give you a few more minutes. Yes, and as Kyle noted, binary search is also it's a type of algorithm known as divide and conquer, which means breaking it down into smaller and smaller and smaller parts. And we're going to talk a little bit about, I won't get into divide and conquer versus brute force versus other types of algorithms, but when you see merge sort, that's a type of divide and conquer algorithm. Binary search is a type of divide and conquer algorithm. Again, you take your data set, you take your data set and you say, where's the thing that I want to find it? It's here. Okay. And then it's here, and then it's here, and it's here. And then you get smaller and smaller and smaller. So instead of like searching over the entire data set or manipulating the entire data set, you only do the parts you need. And divide and conquer is one of the fundamental ways of it's one of the fundamental ways of thinking about problems in computer science. Because sometimes you want to do divide and conquer. If you have, for instance, binary search only works on a sorted data set. Yes, Salvatore, the code should be in the exercise. Brian, who has done this course dozens of times now, he has like refined his code. So I generally just go off what he has written. But he has unit tests built in and everything. And it makes it easy to know if you're doing it right or you're doing it wrong. And about 1 more minute, then we're going to look at the solution. But no, really, it's so lonely in here. Wait, I can show you the room. Giant room here. Giant room here. I'm just in this giant room by myself talking to a computer. If anybody walks in, they will probably think that I've finally coded too far and I've just completely lost it. That's okay. They probably think that anyways, most of the time. All right, I'm going to jump back into this exercise. And we look at the completed. And linear search, everybody, I'm back in the exercise. I clicked on completed, just so we're in this code pen. And linear search looks exactly like you expect. You take an array and it's just a for loop, or you can do a while loop. It doesn't really matter, any sort of loop. And you're just iterating through the array one by one by one. It works. That's more of a brute force way, as in like try all the solutions until you find the one you want. Whereas binary search, being divide and conquer, means take the array and then split it and split it and split it. So the first thing we do is we get the min, which is 0. It's almost always going to be 0 unless you're searching on negative numbers. And we get the array. We get the max, which is the final number in the array. Because remember, the array is sorted, so max is always going to be the last number. And we just set an index. So we can make a loop here. You could, what if you can do it in a for loop? No, a while loop's the most efficient loop here. So we start our index. Brian calls it an index. I would call it a pivot. Actually, a pivot would be quick sort. But let's call it the middle. I would call that the middle. So we're just taking the size of the array, and we take our minimum element and our maximum element, which are the first and last, and we say divided by 2. So we have the middle. And then we set that elements, we set the variable element to the middle. So I want to talk to Brian. He should name things better. That's just called the middle. Element is just middle. So just like the whiteboard example we covered, I'm saying, hey, given this elements, is this thing is it bigger or smaller than the thing I'm looking for? If it's smaller, well, it's just like the new minimum is over here. So it's half the array, and then it's still the minimum, if that makes sense. Good? Yeah. And if it's larger, our new data set is this half of the array. So if it's smaller, left side, bigger, right side. Or if we got lucky and we found the element we're looking for on the first try, then it's just the middle and we just return it and we can exit the loop. So other than Ryan's poor naming system, that's binary search. So I'll just draw it on the board because I'm a visual learner. Again. So all that algorithm is doing, and it looks more complex than it is remember, we're just taking some array, and we're just dividing it in half. And then we look through here, and then we take that, then we divide it in half. And then we take that, then we divide it in half. We divide it in half. And that's all binary searches. Just taking an array of things and dividing half and half and half. But just for bonus, and because everybody's still awake, it's only 1 p.m. here on West Coast time. What if I have this array, 2, 3, 4, and I run a binary search on it, and I'm looking for 3. So binary search algorithm is going to give me 3 as the first element, or 2, depending on if you round up or down. What complexity? What's the best case complexity of binary search? Pause. Let you think about it. Big O1. Big O1 just says it doesn't matter how large the data set is. The best case is I find this on the first try. And that's what big O1 means. That's always what we love to get out of most algorithms, but most of the time you can't get that lucky. It just means I got really lucky and it's the first thing I looked at is the first one. That's what big O1 means. I'm kind of simplifying it down a little bit, but in our case, that's what it means. All right. Any questions on binary search? Can you tell I'm a afternoon person because my energy level just slowly gets bigger and bigger until I'm just yelling at the screen? Yes, big O1 is also known as constant time, which means it doesn't matter how large your data set is. It's always going to take the same amount of time, which is an awesome place to get. A lot of algorithms don't have that luxury, as in they'll split, and then look. But something like binary search, it's just constant time. All right. We're all good so far. Cool. Now let's pick up speed because, man, I am just going so slow and I wanted to teach so much stuff today. I'm so excited about it. Let's talk about recursion. Recursion is this idea, and I'm going to go back to Brian's notes again. Scroll down to recursion. There we go. Recursion is just, it's this concept of doing something, of calling yourself. The common thing to do that people think about is Russian dolls. You know, the dolls that you take off and inside's another doll, and you take it off, another doll, another doll. Eventually you find the candy, or I actually don't know what's at the middle of Russian dolls. Probably just another doll. Anyways, that doesn't matter. Recursion is saying like I have an algorithm. Fibonacci is a popular one. I have some algorithm, and to solve the algorithm, I just need to call the algorithm again with a smaller data set, and again with a smaller data set, and again with a smaller data set, and then again with a smaller data set, until you get to some constants that's either saying whatever it is doesn't exist, or you found it and then you just bubble back up. Recursion is actually, here's a good example of the Fibonacci triangle. I totally forgot what that's called. Fractals are a good example of recursion. Fractals just it's a math algorithm of sorts that makes pretty pictures sometimes. But as you zoom in, you see that the thing is actually made up of smaller elements of itself. So just like this triangle is made up of smaller triangles, and if you zoom in even more, it's made up of smaller triangles. That's the idea of recursion. But the better way to explain that, I can like talk all day about recursion, but the better way of explaining recursion is a common interview question. This is one that I give sometime to, I'd say like medium level engineers. I've got this array of random things, but this array has other arrays inside it. And that's annoying because you can't really operate. I mean, you could, but it'd be a lot of work to operate on this data set when it's an array of arrays. We'd rather just have it one array. So another exercise, this one I'm only going to give you 5 minutes on because it's not too bad once you see the solution. I want you to, and don't click on this link. This is the solution. Make a standard flatten array function, just a flatten function. So at the end, I don't want any arrays. I want one array of all numbers. I don't want any nested arrays. So let's make an array flatten. Yeah, I'll say 5 minutes on that one. And then I'll show you my solution. And then I'll show you the recursive solution, which is shorter. And we'll see why recursion is sometimes super awesome. And it's sometimes it's a pain in the butt. It will drive you mad. And being a good engineer is about knowing when to use recursion and when not to use recursion. And I'm just going to sit here and drink my mango LaCroix while you suffer over my exercises of how to flatten an array. Actually, while you're working, hopefully I'm not distracting, I'll tell you stories of school. So I have a bachelor's of science in computer science. And one of my friends who I've worked with in the past, he has a Bachelor of Arts in computer science. So I always have this endless debate, is computer science an art or is it a science? And it's really both. And part of knowing these fundamentals is knowing when to apply them. And whenever you see someone who's just brilliant, Kyle Simpson's a great example of that, or Kenzie Dodds, like people that they just look at a problem and say like, oh, I know how to break this down into solved problem sets. So I know I'm going to use heap sort on this one, and then I'm going to use a linked list for this one. And you see them break it down, and it's like, it's beautiful to see that in action. And that's what I'd really love everybody to take away is just when you see a problem, just being able to break it down. So it's kind of like an art. You just have to know when to use the right thing. The other hand, it's a science because there's math backing all this. You use mathematical proofs that says like binary search runs in log n time because of this. And there's actually math behind proving why that's the case. It's not just me making stuff up. So it's a bit of both, really. I think a good engineer should have tenets of both. Like you should be a scientist, but you also need creativity too. But anyways, tales from college, tales from Gem's college. CS degree is usually, the really good ones are about 5 years. So 5 years for me in school. And when we were learning recursion, it kind of blew my mind because I was like, what do you mean you call the function itself to call the function, to solve the problem? And we had to actually, for our test, we had to manually recurse through a function and write the output for every single one. So every single recursive step, we had to write what the output was. I'm not going to make you do that today because it's kind of a dumb way to learn recursion. It does make you learn it, but mainly I want to talk about like why recursion is awesome and then when to use it. That's probably more important. And about another 2 minutes on the array flatten. And remember, don't cheat. You'll learn much better, even if you can't get it all, even if you just get stuck and you're just like, if you're ever stuck, just kind of pseudocode it out, the steps in your head. Say like, well, I want to flatten an array. So the first thing I want to do is I want to check the array if there are any arrays in it. Because if there's not, we can just return the array and we'll call it a day. That's our base case. If there is an array, I want to flatten that array. But if there's an array inside that, I want to flatten that. I want to flatten that. And we can do that non-recursively, and then we can do it recursively as well. Right, about 1 more minute. Hopefully no one's stuck. And I should say, this is a common interview question. I've seen it enough times in my life that the array flatten is just like, I don't know, you can kind of do it in your sleep because you've seen it enough times. And okay, let's jump into the solution. Jump to my code pen. And this is a bit more loquacious than it needs to be. Wordy, should I say. So I've got my function here called flatten array, and I have a while loop. Remember how I said in your head, think of the steps that you have to go through with recursion. So I want to take my array. I want to check if it's flat. And if it's not flat, I want to extract the elements out of that array and then put it in the larger array. But I want to keep doing that over and over again. So I have a while loop, and it's checking is flat. Is flat is just a simple function that takes an array, and it just checks over every single element and saying, is it an array? If it is, just return. Return false. And hopefully some of you, because I know that I never remember, yes, array.sum is a real function. Not many people use it, but it is one of the base functions on array in JavaScript. There's also array.every, which is also useful. But array.sum is very, very useful in this case because it's just saying, like, is there any arrays in this? If there's any, it immediately stops and breaks. Probably your more junior developer would just make a for loop and then iterate over that. But array.sum, a little bit more efficient because it's a native code. But so we're just checking, is this array flat? No? Okay, return. If it is, we're going to call reduce on the array. And then we're going to concat the array. So I won't go over reduce because I assume everybody at this level knows what a reducer is on an array. But we take an array, an empty array, and we're just going to concat whatever. We're going to concat all the elements together. And then we're going to check again. And then we're going to check again, and we're going to check again, we're going to check again, we're going to check again. And that's what the while loop does. It's saying, is it array flat? No, flatten it. Okay, check now. Is it flat? No, flatten it. Is it flat now? No, flatten it. And eventually we get the output, it's flat. So that's a non-recursive solution to how to flatten an array. That's okay. But there's a better way to do it. And for this one, we're going to use recursion. And the recursive way is much simpler. It's a much simpler function. So it's just doing everything that my non-recursive way was doing it, but it's just saying, same thing, take the array, reduce it, and saying, like, is this element an array? If it's not, just push it into the holder, the accumulator array. If it is, we're going to concat it, but first we're going to call flatten again. And then if there's another array, so 5, 6, 7, we're going to call flatten again. And then we're going to call flatten again. Then once we're all done, we're going to return boop, 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 all the way back up. And we see, like, the recursive solution in this instance is a much simpler, and it's much easier to reason about what's happening because you just know that it's just calling flatten over and over and over again. Yes, that's the power of recursion. Yes, code does not look good if you paste it in the chat. So a question for you. First one to answer, I don't know. I'll give you a thumbs up because I can't really give you any prizes here. What's the downside of using recursion for solving a problem? Because you might think it's a magical solution. Yes, Sarah, Stack Overflow. That's exactly right. And memory. Yes. But Stack Overflow is probably the main one we're more concerned about, which you can argue is a memory problem, but different topic entirely. Recursion is saying, like, I have the instance, I have all these variables that I have. I have a stack of the work I need to do. And then let's make another stack and another stack, and another stack, another stack, another stack. And we're bubbling down. We go down, 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 down. The problem is if our data set is too large, we can get a stack overflow. Because you can run out of, essentially, JavaScript only has a finite amount in the stack of the amount of work it needs to do. And if you recurse too far down, you'll just overflow and you'll kill the entire system. So we generally probably, we might. In backend Len, we sometimes run into that. If we have extremely large data sets, we can have stack overflow. So before you use recursion, you should understand what your inputs are and that they're not some unbounded input. As in, it's not an array that can have a billion items or it could have 10 items. If you do something like that with recursion, that would actually work. But if you said I have an array from 0 to unknown amount of problems, then if you use recursion, you're going to run into a lot of trouble because you can get stack overflows and you get a bad time. But also, most importantly about recursion is that you need to have a base case. You need to have a part where you break the problem down so small and that you're like, okay, here's the thing I'm looking for. In this instance, we're checking, is the array an array? If it's not an array, we just return it. That's our base case. So everything you have recursion, you always have to have a base case. Otherwise, it'll just recurse all day. It needs to exit at some point. Okay, sorry, I am flying through it because we have so much to cover and computer science is so fascinating. Any questions on recursion before we move on to super, super awesome topics? No questions. Okay. I'm sure everybody has used recursion at some point. It's more of a refresher, and if you haven't seen it before, know when to use it and when not to use it. Remember, if you have unbounded inputs, recursion may not be the best way because you can just end up recursing forever. I won't get into regular expression attacks because those involve running recursive functions, things like that, but not important for today because we have so much cool stuff to cover. All right. Sorting. Why is sorting algorithm always, like sorting algorithms are like almost always on every interview? Not on my team at Netflix. I would never ask, like, why do I care if you know how to sort? But you need to understand why sorting and how they work and what are the implications of different sorting algorithms. But why do we care about sorting? And in this instance, just think purely arrays for now. We won't talk about sorting other data structures, but think of sorting an array. Why does sorting matter? Well, when we want to look something up, remember, if we do it with binary search, we can find something in log n time, which is really, really fast, extremely fast. But first, we have to sort the array before we can run a binary search. Now, if you want to run a linear search, you don't have to sort things. But again, linear search runs in big O n time, which is not great. It's okay, but it's not great. So that's why almost all data sets that involve searching, you got to sort it first because it's always faster to sort and then search if it's a large enough data set. Actually, it's always faster to sort and then search for the most part. Just take my word for it. I am checking back. Questions. Iterate nice stack. Yeah, I didn't get into generators instead of recursion because generators can be really powerful in JavaScript. There are places you can use them in place of recursion. For example, I have a Fibonacci generator that uses it's a generator that it only calls Fibonacci every time that I need to get the next number rather than using a recursive function. But I won't get into that because we don't have enough time today. I will give you a link to it if you want to play with it. But anyways, sorting algorithms. There are lots of them. There are many, many types of sorting algorithms. My personal favorite is the BOGO sort. There's also shotgun sort. They're the same name for an algorithm. It essentially just says randomize everything in the array and then check if it's sorted. If it's not, randomize everything in the array and check if it's sorted. I love it because the upper bound on those sort of functions or those sort of sorting algorithms are infinite because you can literally randomize things and never have it ordered. Anyway, sorry. It's a bit of humor. It's hard to crack jokes. So there's no one here to laugh. I'm assuming you're laughing. I can hear it over the internet. No, anyways, those are fun. Those are fun sorting algorithms because they don't make any sense. But the two main ones you care about and that a lot of people care about are merge sort and quick sort. They both run big O and log n, which is very fast. It's not log n time, but you can't always get what you want. And log n is about the fastest you're going to get for most sorting algorithms. And you care about merge sort and quick sort because under the hood of V8, which is Chrome's JavaScript engine, or Safari uses, I totally forgot what Safari uses. I knew they use Blink. Anyways, I think Firefox uses Gecko. That might be Safari. Anyways, Chrome uses V8. So under the hood, I think Chrome uses merge sort. Might use quick sort. Anyways, every browser has an implementation of either quick sort or merge sort. So when you call array.sort, it's calling one of these algorithms. And they both run at the same time. So you're thinking like, oh, they run at the same time. Why does it matter which is which? I'm glad you asked that question. Let me draw out. Wait, switch the camera. Let's make sure I can see myself. Yes, Todd, I will post a link to the Fibonacci infinite generator during the next break, and you can mire at its funness. Anyways, whoa. All right. Merge sort is a divide and conquer algorithm. Stand for that. So we have an array. Merge sort says, I've got this array. Let's imagine this array. I've got this array of unsorted items. And what I want to do is I want to sort them. Merge, sort. So what I want to do is I want to break this down. So I want to break this into two smaller arrays. I'm going to break you down two smaller arrays. It's actually two here and two here. That breaks down. That breaks down. Eventually you have. Sorry, I am an engineer, not a drawer. But so eventually you have, it's a divide and conquer algorithm for sorting. So it takes an array of items and it breaks them down individually. And then it says, hey, are you bigger than me? Okay, let's swap. Are you bigger than me? No, let's stay the same. Are you bigger than me? Okay, let's swap. And then you join back together. So it says, hey, are you bigger? Are you bigger? You bigger? So it's called divide and conquer because you're breaking the problem down into all the way down until you get to individual elements, and then you just put them back together until you have a sorted array at the end. That's merge sort. Any questions so far? No questions. Okay, awesome. Because we have so much to cover and there's no time. All right, merge sort. Makes sense. You're breaking down the problem into individual elements. You say, for each element, you say, is this bigger than the other one? And then you just put them all back together, and they're all in order by the time you get back to the top. Does merge sort use recursion? Someone, anybody in chat, real fast. Yes, yes. Oh, who won that one? Todd, you are slightly faster than Nader. Yes, merge sort uses recursion because, again, for every level, we're saying, break this down to two smaller arrays. Break this down to two smaller arrays. Break this down to two smaller arrays, and so on and so forth until we get to the bottom part where there's only one element. Let's put number 2 and 3. I know you can't really see that, but those are numbers. We get to the smallest part. Remember, recursion always has to have an exit case. So the exit case in this case is, can I break the number 1 down any smaller? No. Okay, so at that point, across the board, we are the smallest we can get. So let's put these back together, and let's put them back together, put this back together. That's recursion. That's one of the powerful things about recursion is you're doing this a set of steps over and over and over again. All right, merge sort. And I appreciate Kyle calling out its divide and conquer because that is a better way of thinking about the problem. Instead of calling merge, you can call it divide and sort. No, that's why I'm not in charge of naming things. Okay. And merge sort, again, runs at what? Big O and log n. That's right. I'm sure you all said it aloud. I'm just going to take your word for that. What you're saying is correct. And you're not like petting your cat or something, or your dog. All right, let's talk about quicksort. Quicksort. I always feel like quicksorts, it's not fair in the naming convention because, like, which algorithm are you going to use? This boring one called merge sort, or this one, sorry for the glare, or the algorithm called quicksort? That's like, what kind of car do you want to buy? Do you want to buy that boring blue one, or do you want to buy that super fast car? You know, that's not fair naming. But quicksort is aptly named because quicksort is very quick. Quicksort, again, it takes an array of unsorted items. And what it does is quicksort just says, hey, for this array of unknown length, we'll say 0 to n, pick some point, sometimes in the middle, sometimes not, depending on the algorithm. So pick a point, and we'll just, for safety or for simplicity, we'll just say half. Pick a point, and for everything, so we pick the middle, and let's call it 10. Doesn't really matter. We have this middle element. Everything bigger than this element, let's put on this side. And everything smaller, let's put on this side. And then let's put these back together. That actually doesn't split, but let's think about a split. And the middle part is called a pivot because it's going like this. And all the elements pivot off of this one. And it just says like, okay, swap. Then we check, is the array sorted? Probably not, usually not on the first pass. So we pick another pivot, and then we do it again. And we do it again. We do that over and over and over again until the array is sorted. That seems inefficient, you're thinking, but it's not, because we don't have to go through the entire array and say, like, we don't have to do a comparator against the entire array. So the naive way of sorting an array, you'd say, like, and I won't talk about those algorithms, but you say, like, I have an array of 1, 2, 3, 6, 0, doesn't really matter. The naive way would be saying, 1, are you bigger than 2? No. Okay, stay there. 2, are you bigger than 3? No. 6, are you bigger than 3? No. 0? Yes. So when you go boop, 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 boop. And if you do it that way, you run into an enormous complexity of the cost of iterating the entire array and comparing every single number against every other single number. That's, is that factorial? That's probably factorial time. That's really, really slow. So quicksort is just saying, pick a pivot, and then is it bigger or smaller than this pivot? Put on the left or right side, and then just keep doing that until the array is sorted. Quicksort is probably one of the more pretty ones that are visualized because it just goes. Actually, I have a visualization right here. I think Brian has a visualization. And is, let's switch back to my screen. The sorting, yes. Where is his bubble sort? Won't cover that. Insertion sort, we won't cover that. Merge sort. I want to look at quick sort. Oh yeah, quick sort is it's such a good looking algorithm that it's always fun to watch quick sort. Now previously, I was going to ask you to implement one of these, and we'll make you do merge sort. Let's do quick sort. Actually, no, let's do merge sort. I think merge sort's a more interesting one. But it's a good example of the divide and conquer algorithm, and you see it also uses recursion too. So again, if you click on the link in the notes, if you need me to repost them, I will repost them. I think he has an exercise for merge. Yes, he does. So just click into the exercise and fill out the function for merge sort. And I'll give you, I only have a little bit of time, 7 minutes. So I'll be back at 2:14. Yes. But remember, when you're thinking about merge sort, remember, you're taking an array, you're splitting it in half, and then you're checking, is this array, are we down to one element? Can we split this anymore? If we can split it more, split it again, split it again, split it again. And then, so that's the splitting part. and then we're putting it back together. So we're dividing an array into, doesn't matter how many subarrays, until we can't divide anymore. And then once we can't divide anymore, we take those two sides that we just split, and we put them together in order. And then we take those two arrays, and then we put them together in order, and we put them together in order until at the end we have a completed array. This one, I think when you see it, it sounds more complicated than it is. And a lot of algorithms are like that. They sound far more complex than me explaining on a whiteboard once you code it out, which is why doing the exercise is important. You'll see like, oh, it's literally just splitting arrays and putting it back together. That's not that hard, Jem. I'm like, yeah. I forget who invented merge sort. I should look that up. Probably someone very smart. Yes, thank you, Kyle. Kyle just posted a link and his book, which to this day, everybody's like, oh, have you read Kyle Simpson's book? It is a very, very excellent book, and he covers recursion. Recursion, we can go to so much detail about recursion. So many nightmares. Sorry, I'm just thinking back to school. It's getting that 1,000-yard stare. Recursion. All right, about 3 more minutes. Hopefully, you're giving this a good shot, or you're just hanging out, marring my beard, the blue shirt. Great point, Kyle. Yes. So what a lot of people don't know is an ES6 or ES 2015, 2015. There in the spec, there's actually a call for tail call recursion. And what that means is if you have a recursive function that all it does is at the end, it returns a call to itself. It doesn't increase the stack if implemented properly. So remember we talked about stack overflows when you recurse too many times. If tail call recursion is properly implemented in the browser, you can recurse indefinitely. Well, I guess indefinitely, and you don't increase the stack. So you're not going to get a stack overflow. Unfortunately, in the year 2018, the only browser that I know of that has properly implemented tail call recursion is, I know you're thinking Chrome. No, Safari. Safari is the only browser. Oh, Adrian, so fast. Oh, and Kyle, you all are so fast. Yeah, Safari is the only browser so far to implement tail call recursion, which is annoying because other languages other languages have tail call recursion properly. So like you can do recursive over large data sets, and you're like not worried about a stack overflow. Unfortunately, the other browsers are lagging. I don't know what they're doing. Probably just hanging out, drinking lattes. I don't know what browser people do. And got about another minute on. Oh, interesting. So I wish Kyle had a microphone. We could have a good conversation. They're refusing to implement proper tail call recursion. Do you know why? I should talk to them. I say talk to them, but like I don't know them personally. But there are occasionally TC39 meetings here at Netflix, and if you get a chance to sit in one of them, you just happen to know somebody or they're around. It is a fascinating topic on how JavaScript gets created and the idea and the history and just the semantics that go into creating even the smallest feature. You would be amazed how much detail goes into it. But anyways, it's a fun experience if you get the chance. Creates complications in their code base. That's why they don't want to implement tail call recursion. Well, cross-window tail calls. Interesting. I can see that, but I don't know. I'm surprised Safari did it, but Safari tends to take longer on things. But when they do, it's usually a solid implementation without a lot of bugs. Generally, I'm not the biggest fan of Safari because they tend to be slower on being standards compliant. But in this case, it's pretty awesome. All right, enough about politics of JavaScript. Yes, there are politics in JavaScript. So let's look at the solution to merge sort. I won't spend too much time on it. I'm just going to cover the base parts. So we're getting the total length of the array. That doesn't matter. We're getting the middle. So in this case, for his merge sort, we're just taking the exact middle. So the middle divided by 2. We have a left array, so we're slicing, and we have a right array. And then we're just calling merge sort again recursively on the left array, and then it's going to go all the way down until it hits 1, until there's exactly 1 element. So we could actually just say, no, so length equals 1, but it doesn't really matter. And so once we have 1, we're going to wait, and then we're going to do the same thing for the right side. So it's going to split and then split and then split again. And then once it's all done, we're going to call merge on every single. We're going to call it merge on every single iteration. So, but at the end, this will be merge on 1 and then 2, assuming the number 1 and 2. So we're saying while there's a length, so while it's not 0, push the results to array. So it's sorting on the fly. This is where the sorting part comes. This is divide. This is the conquer. Divide and sort. No, it's not a real thing. Anyways, we're pushing the array. If it's bigger or if it's smaller than the one on the right, push it to the left. If it's smaller, so I won't get into details because I have 45 minutes left and so much more to cover. But it's saying if it's smaller, put it together, or swap them and then put it together, and then just put these together, put these together, put these together. So you have this blob that grows and grows and grows, and by the time you're done with your recursion, as in like all the calls are done, you're back up at the top of the stack. It's sorted. And it's when you look at it like in that terms of just breaking it down and dividing it smaller, 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 then putting it together, merge sort isn't really that complicated. So I know what you're thinking right now. Okay, I've got these 2 algorithms. I've got merge sort. I've got quick sort. We didn't do an example for quick sort, but there is one on Brian's page right here if you want to take a look at it. So why are there 2, and why do some browsers implement quick sort? Some browsers use merge sort. Well, in algorithm terms, there is something called space complexity, and there's something called time complexity. A lot of times, most people, they only think of time complexity. They think, how long does something run? Because computers are cheap, and memory is cheap, and hard drive space and is cheap. So we don't think about the memory complexity of something. But with merge sort, all right, I'll just ask you this question. Which of these algorithms, quick sort and merge sort, we both know how they work now, hopefully. Which one is going to be more memory efficient? Yes, everybody. Yes, exactly. Everybody has that right. I don't even know why am I teaching this class? You all are so smart. Yes, quicksort is going to be more memory efficient because merge sort, remember what it's doing? It's creating, let's go back. Here, we're creating an array. We're creating two arrays. So every time we split, we're creating another array. We're creating another array. We're creating another array. We're creating another array. So merge sort, while it's fast, it's big O and log n, it's going to use a lot more memory than quicksort because quicksort doesn't create new arrays. It takes the arrays in place and just swaps the elements around. Whereas merge sort breaks these down every single time. And it depends on what's the limitations of your system. And being a good engineer is about knowing like the trade-offs you're making and the limitations of the trade-offs that you can make. Merge sort is very fast and it's a fairly straightforward implementation, but it does use more memory than quicksort, which is why a lot of people kind of defer to quicksort. But in the end of the day, it doesn't really matter that much for most instances that we're ever going to use them for. But it's good to know about both of them. It's good to know the runtime. And again, if you're curious about all the other sorting algorithms that we didn't talk about, Big O cheat sheet is very helpful. Like I said, there are a lot. I don't see BOGO sort in here. But if we do, if you ever look it up, it's a fun implementation because you can do it like a million ways. Essentially just like randomize something and see if it's sorted, then you randomize it again. Okay, so we've learned these two sorting algorithms, and we've learned kind of the trade-offs you make when you use merge sort versus quicksort. Let's talk and kind of wrap up with data structures because before I move on, are there any questions? Merge sort data. Order of equivalent elements. Yes, we didn't get into stable or not stable. Essentially, it's just saying if I have an array and it has the number 2 and it has a number 2, can I guarantee that this number 2 is going to be in place of this number 2? As in, like, that's in place. It's going to keep it in the same order that you have. It doesn't necessarily mean that, it guarantees the order of the elements, even if they're the exact same element for comparison's sake. Sometimes you care about that. Sometimes you don't. That's like a bit more detail that I want to go into today. But when you hear someone talk about stable and in place and things like that, that's what we're referring to, is the order of the elements when you sort them, the order of the same elements. Oh, yes, Kyle makes an excellent point, as usual. Merge sort is stable, so the order of the elements is going to be maintained. So if you have a 2 and a 2, when you break it down, the 2 that came before is always going to be for the other 2. Quicksort is not. But again, quicksort is more memory efficient, whereas merge sort is stable. And it depends on the application that you're using, why you'd want to use one or the other. But excellent points. This is such a great class. I wish everybody was here because I would have such a great discussion. I'm sure I'd learn a bunch too. But any other questions on sorting algorithms? Nothing. Okay, let's talk about data structures. I like data structures. Data structures are, one, it was probably the hardest class I took in college. It was known as the washout class. Everybody takes CS 101. You do some like intro to programming. You do some like basic database stuff. Then you get to data structures. Data structures was the class that separated people from being a computer science major from being some other major. It kind of filtered out a lot of people because data structures are hard because you have to think about like, oh, what are the implications of using this data structure and this data structure? But at the core, it's what's the shape of the data on the computer, or what's the computer think the shape of the data is? And this is important. Mainly today, we've been talking mostly about arrays. We understand arrays. Arrays are a fixed length data structure, and where everything has a pointer to the value. And the pointer is just the index. So index 0 equals some value, so on and so forth. I won't go too much into arrays because Hopefully, by the end of the day, you know what arrays are. If not, I'm sorry. I feel bad for you. But so we talked about arrays. In JavaScript, most people only use arrays or objects. Those are the two data structures that they care about. I'll talk about objects a little later, but fun fact, an object is not a data structure. It is a representation of some underlying data structure, but an object itself is not I wouldn't say it's a formalized data structure, whereas arrays and maps and sets are formal data structures. Any questions on arrays? No? Do you have a joke about famous arrays pizza? No, but I should have next time. Next time I'll think of jokes about data structures. Arrays, famous pizza. I'm assuming you're laughing at home. It's really hard to tell jokes. A set came into JavaScript natively in ES 2015, and sets are pretty cool. A set, I don't want to complicate things. I want to be like, it's like this data structure, but not, because that's a terrible way of defining things. A set is a data structure that guarantees that there are no repeated values in the data structure. And what's a real useful example of that? Let's thinking. All right. Here's one. Let's say I say, man, these employees at Netflix, they are so lazy. They take so many bathroom breaks. And the problem is, like, I don't know when a bathroom is occupied or not. Okay. So let's create a set of every single bathroom in Netflix. And every time someone goes into a bathroom, let's just flip that to true. Actually, yeah, every time someone goes into the bathroom, let's just add that to our set. So we have a fixed number of bathrooms at Netflix, and every time someone goes in, we say it's true. Now, what if two people go into a restroom or a restaurant? I shouldn't use bathroom. It's a weird example. But let's say two people go into a room. Well, we don't necessarily need to know that two people went into a room. And that's what a set is good for, because we only care about if it's true or if it's false in this particular instance. And we don't need to constantly update it. If we had an array, we'd have to make an array of items and then like flip the switch for every one and then check if it's not there. Then there's two people in this room. It would get messy. But a set means if you add it and it's already there, it doesn't increase the size of the set. And that turns out to be really useful because for just that random example I gave you of bathroom set, but like you can add data into a set and it won't blow up the set if the data already exists and it's guaranteed. That's super, super useful. What's another real life example? Can anybody think of other real life examples? I'm blanking right now. But anyways, a set means you can throw data into it and it guarantees it won't be duplicated. So it's going to be more memory efficient than a lot of other data structures if you're just stashing a lot of data. Okay, that's a set. There is a link. I think Brian has a link in there. Yes. I think he covers sets. Yeah, he pretty much says the same thing that I said. It's a black box you can throw stuff into, and data won't be guaranteed, so you're not going to run out of memory. Well, I shouldn't ever say you're not going to run out of memory. You're less likely to run out of memory using a set. That's pretty cool. Let's talk about maps, because I think maps are more interesting, actually. Jump to a map. A map is, Brian's saying it's quite similar to JavaScript objects. Yeah, we're going to talk about objects and maps when we talk about hash maps towards the bottom. But a map is it's exactly what it sounds like. You have a key, which can be, in JavaScript, could be anything other than a primitive. So it can be an object, and you just map it to some value. That's it. It's kind of exactly what it seems like. And you're saying, are maps, is a map an array? No, because arrays use primitives for lookup, so they use numbers for the index, whereas a map uses objects. And you can't use a symbol as a map key, because I have tried. I had this awesome idea about weak maps and using symbols, and it was going to be awesome, but you can't do that in JavaScript. I won't dwell too much on maps, because when we get to hash maps, they'll probably make a little bit more sense. Okay, I should slow down. Is there any questions so far? Adrian says, "Is a map is faster to look up because it's literally just the key. So think of instead of iterating over array, if you knew exactly where that item was in the array. So just index 5, you just pull it out. You usually can't do that because you don't know where it is in the array unless it's a sorted array. But even I won't get into that. But yeah, think of looking up a map as like just a pointer to the exact value. Map lookups are very, very fast because you already know where it is. You have a bunch of keys and you know exactly where that data points to. Anybody else questions about maps? Cool. Let's talk about stacks. And no, I don't mean stacks of pancakes. I can go for pancakes right now. It's like 2:30, but I could eat. A stack follows the last in, first out. So what's a good real life example of a stack? Stack of pancakes. Actually, a stack of pancakes works pretty well. If I have a stack of pancakes, you can tell I'm getting hungry. If I have a stack of pancakes, I put one pancake down, I put the second pancake down, and I put the third pancake down. I have the stack. What's the order that I'm going to consume these pancakes? Well, obviously, I'm not going to pull from the bottom and then pull that one out and then eat that and pull that one out and then eat that, pull that one out. No, I'm going to pull from the top. And that's exactly what a stack is. So next time you're thinking like, what's a stack? Think pancakes. It's last in, first out. So the one that comes in first is going to be the last one that is consumed, especially with pancakes. So as you manipulate a stack, it's called popping, and you do something similar with an array. But you pop the element off, you pop it off, you pop it off, you pop it off. And stacks are important when we think about JavaScript execution, a lot of program execution, but we think about recursion. Recursion has a stack, and it's saying, like, here's our base case at the bottom, and then let's recurse again. Let's add something else to stack. Let's recurse again. Let's recurse again. And eventually you have this call stack that's this high. We hit our base case with recursion, and we pop everything off, returning until we get to the bottom, and the stack is clear. In a very loose sense, that's exactly how programming languages work, or JavaScript in particular. You have a stack of items, and you just pop the items off. When you're done, it stops working. Did that make sense? Because I am flying through. These all deserve like far more time than they do. Stacks have now become my favorite data structure. Stacks are pretty cool. Yeah, again, the real life example is eating pancakes, but a more applicable example is JavaScript and the stack. Actually, yeah, that's where, if you ever heard the term stack trace, that's exactly what it is. You have the stack of calls that the call originated here. A stack of cows. I don't know, Kyle. Stack of pancakes, man. Stack of towels is good too. But for instance, when something breaks in your program and you have a stack trace, there is a base case that started the call, and that called something, that called something, that called something, that called something. Eventually, the error lies hopefully in the top of the stack, where the actual implementation has. But the stack trace tells you exactly where that came from, and that's a stack. That's exactly right. Kyle's is saying grocery store shelves. Kyle's saying you put your linens in the closet and you take the top one off. That's exactly right. That's a stack. And it uses last in, first out. Let's talk about Kyle. My stack of pancakes are like this big. I go hard on breakfast. It's my favorite meal of the day. I don't eat it often, but it's like this big. Let's talk about queues. A queue is first in, first out. A queue is the best real world analogy I can think of is think of a line for the bathroom. No, think of a line for a movie. The first, or a concert, doesn't really matter. The first person in line is the first person to get popped off, and then the second person, and the third person. And the great thing about a queue versus a stack is I can keep pushing things into the queue and then consuming them. And a queue is it's a very widely used data structures when you're talking about consuming jobs. So if you have something like you have a bunch of jobs running through Zookeeper, and they're all queuing up in like RabbitMQ or something like that. You're popping things off the queue, and you're doing the jobs that come in. So it's first in, first out, just like a line or anything else that involves the person going first. The first thing that happens, the first thing that enters the queue is the first one that gets taken care of. And you can just keep pushing things into the queue indefinitely, as long as you're popping them off. If we wanted to build like a buffer as a data structure, something that's always going to be filled with data, a queue is a great use for building a buffer. So a buffer is just saying, like, for instance, like a video player at Netflix using a buffer. It's just saying, like, I have these chunks of video, and as we're playing, we're just popping things off that buffer, and we're just putting more things into the buffer so that you always have, you're never like waiting on network latency. That's how a lot of the internet works, is working on the queue-based system. But queues to me are, to most people, they make a lot of sense when you explain a real world implication. So waiting in line is the great example of a queue. And yeah, a queue's used, like I said, pretty heavily in a lot of programming, but as are stacks, but probably queues a bit more. Let's see. These comments are great. I should like do a Twitch stream, because like just for the chat alone, this is amazing. And okay, any questions about a queue? Last in equals push, first out equals pop. Yeah. Yeah, that's a good way of thinking about it. Let's see, JS red, push and pop. Yeah, you could think of a, well, I sometimes make the, I draw the conclusion, or I draw the connection between arrays and a stack and a queue, because stack and queues are not data structures in JavaScript. So if you implement them, you're going to probably use an array. But with an array, you can access any element at any time, because we have index, we have pointers to all the values. Whereas a stack and a queue, you can't. You can either access the first element only, and you just push things to the queue, and you have to consume the whole queue to get to a certain point. Whereas an array, you can jump around, or a map, you can jump around. So I try not to make that, tie those data structures together. If we had more time, we would build a queue out of an array, and it would make a bit more sense. Nader asks, with JavaScript, do you know if shifting an array is inefficient? No, but every time you shift, you're actually creating a new array. Because remember, array is unlike a set or a map, it is a fixed data structure. Arrays have a fixed length. And that length, that's why you can always reference array.length at any given time. And you know exactly how many items in that data structure, because the array itself keeps track of how many elements are in it. So every time you shift, you're actually just making a new array. Yes, you do copy over all the elements. It's pretty fast under the hood. Big O N. Yeah, you can say it's big O N. It'd be like n-1 big O N, but like that's not important. Big O N is probably the right way of thinking about it. But that's why with something like a map or a weak map or things like that, you can say size of, but you can't get a fixed length, because actually weak map is probably a better idea. But there's no fixed length because it grows dynamically, whereas array is not dynamically sized. Array is a fixed length. Okay, I don't want to go too far down the rabbit hole of fun data structures, because they are fun. What's the next? Covered stack, covered queue. Let's talk about a hash table. Yes, so I think Ryan has notes on there. Array list, boring. Linked list, talk about that. Does he talk about hash table? I think he does. Wait, does he? He just has cooler visualizations. Okay, so this is a real interview question that I've been asked. It was under the hood. Remember how I said an object is not necessarily, it's not a real data structure? So under the hood, they said, Jem, under the hood, what is an object represented as? And I said, well, it's a hash map or a hash table. which is true, yeah, especially in V8. Try to find the code somewhere. Someone had the source code. This is pretty interesting to look at. But under the hood, an object is just a hash map. So every property in there is just a hash, which points to a memory reference somewhere. That's why if you have a very large object, you can't think of them in computer terms. You can't think of like the memory blocks as contiguous, as in they're right next to each other on the disk. They just point to random memory locations. So if you want to sound really smart at some point, just think object under the hood is just a hash map. And a hash map is just saying, I have these keys. So let's say the key is my name, Jem. The value is my last name, Young. And what we're going to do is we're going to apply a hashing function to the key. And that just makes it easier to look up later. I don't want to get into hashing. Assuming I'll just quick poll the rooms. Everybody understand what hashing is? Yes? Okay, yeah. You all are like on top of it. It's great. So I won't explain hashing, but hashing is just, or a hash table is exactly what you think it is. It's just a bunch of hashes and they all point to a different, they just point to a memory address somewhere. And the hash is usually actually the pointer to the memory address. In JavaScript, it doesn't make as much sense because we don't have pointers, whereas other languages like C or C++, they have actual pointers to the actual memory block somewhere on your computer. Does that make sense? Awesome. Okay. Thank you, Todd. Hopefully it makes sense to everybody else. But yeah, so when you think of JavaScript, think of JavaScript objects, think of they're actually hash maps under the hood. What are the implications of using a hash map instead of something like an array? Anybody? Bueller. Yes. Both right. Nader and Adrian, you're both right. The beauty of an object or a hash map versus, say, an array is, yes, both of you high five. It's me, high five, is that it's not a fixed size. We can grow an object instantaneously, and the lookup time is going to be exactly the same. The lookup time is fixed because, remember, all those keys are just hashes to some memory reference somewhere on the database, but we know what the keys are. So instead of saying, like, are you the thing I'm looking for? Are you the thing I'm looking for? Are you the thing I'm looking for? We just instantaneously point it up. That's why accessing objects or accessing properties on an object are really, really fast because they're just pointers to exactly the memory location. Versus an array, you have to either iterate through the array or know where it is ahead of time. And the best part is they're not a fixed size because they don't have to sit in the same place on the computer in your memory. They can sit in completely different places, but because we just have a pointer that says like, hey, it's over there, or hey, it's over there, the lookup's instantaneous and the object can grow at any rate. That's why you can't say object.size or object.length because that doesn't really make sense. What we can do is we can say object.keys.length and count the number of keys in an object, but we can't directly say an object is this big because it has no concept of bigness. It has pointers to everywhere. Hashing is used quite a bit throughout all of computer programming. We won't. I think Brian said he wanted to cover. What is it? He said he wanted to cover something. Totally blanking on what he. Sorry, it's been a long day too. I am blanking on. I'm just gonna look it up real quick. Oh yeah, that's what he wanted to cover. I think Brian wanted to cover bloom filters today. Whoops. Feedback. Yeah. I will talk about bloom filters. Personally, and this is my opinion, it's where he and I might differ a bit. I don't think the real life value for most engineers is there. I will talk about what they are, but a bloom filter is just you're putting things in and you're hashing the keys and you're storing that hash. That's all it is. Actually, got a little bit of time before we covered linked lists. So, all right, I'll talk about a Bloom filter. See if there's notes. I think he might have notes somewhere on Bloom filters. He does. This one. All right. You can see the completed code if you want. It's actually not too bad. But a Bloom filter it's a probabilistic data structure. No, I'm not making up words to make myself seem smart. That's a real term. So a Bloom filter can tell us if something is not in the data set. And you're like, well, that's not useful, because most of the time when you're trying to look up some value, you want to get that value out, or you want to know if it does exist in the data set. But a Bloom filter can't really do that. I mean, it could, but it's not very good at it. It can tell you definitely if something is not in a data set, but it can't tell you for sure if something is in a data set. So actually, let's just walk through the code. It'll probably be easier to explain. So Bloom filter, it's very fast for saying like if something is not in a set. So what we're doing is we're taking a string, or actually any object really, we're hashing that into, in this case, he's using 3 hashing functions. What is he using next door? Yeah. Well, he's using 3 hashing functions. So he's breaking a string up into 3 parts. So the great thing about a hashing function is it doesn't matter how long your string is. It's always going to be a fixed size once you hash it. And that's what's really awesome. That's how passwords work. If you're ever wondering, like, how is this password hashed to like 64 characters when my password is actually Hunter2? Oh, crap, I just told you my password. No, that's because when you hash something, it's always going to be the same size generally every time. So we can take a string that's really, really long, break it up in 3 parts, and then hash it, and then those keys are always going to be a fixed size. Or we can take a really, really short string, hash it, and because you can hash zeros, you can hash emptiness, it's always going to be a fixed size. So we take these 3, we hash the string 3 times, and see, that's why I didn't want to get into Bloom filters, because depending on how many times you hash something and how many parts you break it into, depending on your collision rate, things like that. But the best example, actually one of the better real life examples was, where is he? Oh, I saw a good one. Yes, there's a Medium article on their real life use case for Bloom filters. And I just want to find their diagram because I think it's pretty cool for explaining. And it has something to do with dogs and cats. But, don't worry, we're almost at the end. I'm sorry if your brain is hurting. You've learned from so many smart people today, and now we're talking about hashing, and you're like, what? What is even happening? Don't worry, it's Friday. You can relax after this. There we go. So it's a perfect example. Their hashing function, they want to hash the word cat into 3 different buckets. So they split it, and their hashing function, it doesn't matter what it is. It breaks it into 3, 4, and 10. When they hash again, they have different buckets. So they hash dog, it's 1 and 2 and 5. Cool, no collision so far. So now they hash the word elephants, and it ends up in 10, which is a bucket that has already been hashed into. So that's why a Bloom filter is actually it gets even more complicated. That's why a Bloom filter is a probabilistic data structure. It can't tell you if something exists, because remember, if you hash something and the hash actually turns out to be equal to some other hash of some other objects you had, instead of colliding like you normally do with a normal hash table, it just says like, okay, this already exists. I'm not going to write anything new in there. But if I go to look up elephant later, I can't say definitively if elephant exists in the data structure or not. I can tell you if, say, sea monkey, not a real animal. I guess it is. I can tell you sea monkey does not exist in the data structure, because if I hash it and all the buckets are empty, then I know that it does not exist. But if I try to look up dog, I can say like, yeah, it might exist, but it could be something else entirely. And the useful Medium has a good use case where they said they have a large list of articles that they want to say like, hey, has Kyle read all these articles? We don't know, but we want to know definitively the ones that he has not read. And that's what a Bloom filter is good for. So rather than iterating over every single one and be like, has he read this? Yes. Has he read this? Has he read this? Has he read this? Let's just get articles that we know for a fact he hasn't read. And now you see why I didn't want to get too much into Bloom filters, because the real life case that if you implement, it's not going to be that often. You can say for searching strings, but there's probably a better data structure for that. So a try is probably better data structure for searching a large amount of strings. But now you kind of know what a probabilistic data structure is, why a Bloom filter can tell you something's not in it, but it can only tell you if something might be in it. Okay, I will talk briefly about hashing. So hashing in college was, oh man, we spent probably a few weeks covering hashing, because there are different strategies for hash tables. So depending on your hashing algorithm, you say like, hey, I've got, I don't know, I've got a list of everybody in the room. So I've got Adrian and Todd and Nader and Kyle, and I've got all these people in a room. And I want to say, well, I don't want to store every single person in the room, because let's say this is a super popular course and there's 200 billion people. I don't know how that happened. There's 200 billion people in this room. Storing every single person in the room doesn't make sense. So what if we can just hash them by the first letter of their name? And that way we can actually, no, sorry, I don't like that example. I want to talk about hashing and collisions, but actually that works. So if let's say again, sorry, rolling back, if we're hashing everybody's name and we put in this giant hash map, what happens if I hash the word gem? There's also my evil twin, Jom. What if we hash to the same location? We have what's called a collision. And this is where hashing and hash tables get really interesting. So you want to set your hash table is a fixed size. So every time you hash something, it's going to go here, or it's going to go here, or it's going to go here, it's going to go here. But don't think about Bloom filters, just ignore those for now. But your standard hash table, you don't want any collisions, because you want everything to hash to be unique. A good perfect example is objects. So we said objects are just hash maps underneath. What if you had something that hashed to the same, you had something called property on an object called value is foo. So what if our hash table is small and our hashing algorithm is weak, so that we had a value called bar, but they both hash to the same value? That's not useful, because you objectively, you literally set an object equal to this, a property equal to this, you set another property equal to this. They shouldn't point to the same memory address because they're different. We can solve that by choosing either making the hash table really big and making our hashing algorithm really complex, so that it doesn't matter what I hash, it's always going to be a unique value. Or we can make it really small, which means it takes up less memory, but we're more likely to get collisions. And a collision just means that something hashes to the exact same hash. The problem with that, so it's a trade-off, right? It's a trade-off between allocating a lot to your hash table and making a complex hash, or making a smaller hash table and chancing on collisions. It's kind of complicated to explain in a short amount of time, but it's actually a hard problem in computer science, because remember, the more memory you allocate to any given function, the less memory is available for other processes. So you can just say like, oh, I want to make a hash table and I want to make it arbitrarily large. Well, what are the other programs going to use at that point? But if you make it too small, you have collisions, which means you literally have to rehash everything in the, not rehash everything, but you have to move everything in the hash table to a bigger hash table and then recalculate the hashes, which is expensive. There are different complexities around different hashing structures, things like that. I can tell you in college, we had to calculate these manually and say like, it's going to collide after 4 iterations of a hash. And yeah, it's far too long of a day to get into that. But those hash tables, we talked about Bloom filters, but just remember, if nothing else, and this will put you probably leagues ahead of most JavaScript developers, under the hood, a hash table or an object in JavaScript is just a hash map. And the benefits of that are instantaneous lookup, because it's just a pointer to a memory reference somewhere. And if you store two objects like object.value equals foo, and I try to add another property called object.value equals foo, in JavaScript, it's not going to create another, I mean, you probably already know this, but it's not going to create another property on that object because it's just going to hash to the same value. That's the benefit of using a hash map, is that the same values are not duplicated over and over again. Woo! That was a lot. All right, I'll cover linked lists because I think they're pretty cool. And then that should wrap us up. Linked list. Cool structure. I don't know why I click on this. It's like, it doesn't take me anywhere. Scroll to the bottom. All right. I'm going to draw a linked list because in my head, I think it's easier. All right. Linked list. Whiteboard. A linked list is, think of it as it only has 2 points. It has a head and it has a tail. It has beginning and end. All the other values in between, it doesn't really matter. So a linked list is made up of nodes. Node. A node for a single linked list only has 2 properties. A next, so it points to the next value, and a value itself. So we can say, so you can see that. Value and next. And next is actually just another pointer to another node and another node, and so on and so forth. So as we look through, we can iterate through a linked list very quickly because it's just next, 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 next. And then when we find the thing we want, we can say, give me the value. And at the top of the linked list is called the head. And again, this is just a node. What I personally find fascinating about LinkedIn, or not LinkedIn, that's so awkward. What I find powerful about linked lists is that, one, it's really simple when you think about it. When you think about it, it's just a node that has a value and a pointer to the next value, or a pointer to the next node. But you think about it, it's kind of like a tree in a way. I mean, they're completely different data structures, but visually in my mind, I see it as a tree because a tree is a similar data structure, but it just has a value. Depending on the type of tree, I won't get into that. And that just points to another node, which can point to another node. And a tree can have 2 children, and each leaf can have 2 children, blah, 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 blah. I won't get into that. But when you draw them out, like for me personally, the idea just makes sense. It's a data structure made up of smaller data structures that just point to each other. And that's what makes linked lists just really awesome, but also simple too. Because at the core, it's just a node with a value and a next. Saying, okay, that's cool. If I start at the head, I can traverse an entire list very quickly. How do I go the other way? I'm glad you asked that. We can have a doubly linked list. So again, we just have a node. It has a value and a next. But instead of next, or along with next, it just has a property called previous. And all that does is just a pointer to the node before it. And that's a doubly linked list. And why do we care about linked lists? It's because they're fast. It's very, very fast to iterate through a linked list because these can be anywhere. And these nodes can live anywhere because this is just a pointer to a memory address somewhere in the system. They don't have to sit next to each other. So we can just say head, next, 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 next. Or we can start a tail and say previous, previous, previous. Or we can start at a node and say next, previous. We can go any way we want to go. But that's why linked lists are really, really cool. And they're used quite a few places. Thank you. Pancake time. We have 3 minutes. Oh, yeah, we do have a hard cutoff in 3 minutes. So I will not go into the exercise for a linked list. Actually, we can look at it real fast. I have an invitation of linked lists, which I need to share out. But it's much simpler than this. I think Brian makes it really complicated. But he's a really smart guy, so that's okay. But my advice for learning data structures is like program them. I have a link somewhere. James Kyle has like a link to a bunch of tiny data structures. And once you see how they're implemented and you understand like a node has a value and it has a pointer to either the previous or the next node, that's it. Like that's literally all a linked list is. And it's just made up of a bunch of those nodes. It's really simple. But if you got asked this on a whiteboard question, you'd be like, linked list. I don't know. But when you draw it out in your head or on a whiteboard, you say like, oh, I can code that. I can start it here and this create a pointer to another node and create a pointer to another node. It just becomes much simpler in my mind. Everybody has their own learning style, but that's my style. All right, we have 2 minutes because there is a hard cutoff, I'm told, because it will just kick everybody out of the room. Are there any last questions in these last 2 minutes? Oh, thanks, Todd. Thanks for sticking around, all of you. I know it's been a long day and we've covered a lot of disparate topics. Hopefully this whets your appetite a little bit for learning CS and learning why they're important. The fundamentals, like you'll see so many times, and at the core of most things we use, actually at the core of all the programming and things we build are these data structures underneath. It may not seem like it, but once you drill down and you drill down, you see like, oh, an object's just a hash map at the end of the day, or that's just a linked list. It becomes much simpler to kind of understand. Brian, I should throw in a link. This is actually a href link to something. But he has a course called 4 Semesters of Computer Science in 5 hours. Then he has a part 2 where he goes into much more detail and like has better drawings that you can actually see. And while his beard is not as awesome as mine, he's really smart. So that's on Front End Masters. So I encourage you to check that out. Check out all of Kyle Sims' books, because if you read those, master those, you will be a JavaScript pro by the end. I guarantee it. For anybody else, hit me up on Twitter if you want, @JemYoung, and I will do my best to answer your questions. But above all, do the exercises. You will learn much better if you actually do them yourself rather than just like copying and pasting, because you'll understand like these algorithms are not that complicated at the core.
Thanks for watching.